So today we're going to be looking at the reaction rate and temperature. We're going to review some important things about the rates of reaction, and we're going to go over the theories behind reaction rates. And then we're also going to look at how the reaction rate is impacted by changes in temperature. So, reviewing what the rate of reaction is, the rate of reaction describes how fast products are produced and how fast reactants are consumed. Essentially, the rate of reaction just tells us the rate at which the reaction occurs. We can relate the rate of reaction and the concentrations of reactants using a rate law, which takes the form rate equals K times A to the power of M times B to the power of N, and so on, so on, so on, depending on how many different reactants we have in a particular reaction. So, K is the reaction coefficient. This is determined experimentally, and it changes depending on the reaction. For a particular reaction, it may also change depending on if there's a catalyst or if there is a change in temperature. The reaction coefficient will also change. A and B are the concentrations of reagents. We may have A, B, there may just be a single reagent, which will just have A, or there could be 50 reagents, and then we will have a very long rate law. M and N are the required exponents. It is important to note that M and N are not the coefficients in a reaction necessarily. They're just required exponents that we put with the concentrations of reagents. These are also determined experimentally, and we use them to determine the order of a particular rate law. Transition state theory. This is an important theory for rate laws and how rates occur. So this theory suggests that in the process of reagents becoming products, a hypothetical species will exist in a transitory state. The stage of the reaction is the transition state, and the hypothetical species is the activated complex. So in order for reactants to become products, they will very briefly enter a transitory state that has a much greater energy than either the reactants or the products. The difference in energy between the reagents and the activated complex is known as the activation energy. This is the energy that the system needs in order for the reaction to proceed. So here we have a reaction process diagram where we see how the reaction occurs. We start at the reagents that have a specific amount of potential energy. They will have an increase in potential energy to reach the activated complex, and then a decrease in potential energy to reach the products. We see that even though the enthalpy is the same for the forward or reverse reaction, the activation energy, which is represented by EA, changes depending on the direction of the reaction. So for the forward reaction, it takes however much energy to reach the activation complex, and because the products and reactants are at different energy levels, it will take a different activation energy depending on the direction of the reaction. So the activation energy is the energy that any reaction needs in order to proceed. Collisions are how reactions occurs. When molecules collide, they may end up causing a chemical reaction. Collisions occur very frequently between molecules, but often collisions are ineffective and do not lead to a chemical reaction proceeding. In order for a collision to be effective, the molecules need to have enough energy to overcome the activation energy of the reaction, and molecules must be in the correct orientation. So if molecules are moving too slow and they have the incorrect activation energy, they don't have enough energy to overcome the activation energy, then the collision will be ineffective if they're colliding at too slow of speeds. As well, if they're in the wrong orientation, then the activation energy, then the collision may not be effective. So here we have, showing this in a diagram, we have two molecules, and when they collide, they have the products here, whereas in a different orientation, this is the incorrect orientation. When they collide, no reaction occurs. So they have to be in the correct orientation, and they have to have the right activation energy. So how does temperature impact the reaction rate? What it comes down to is the activation energy. Temperature is also the kinetic energy of all the molecules in a sample. At a greater temperature, there is greater distribution of energy among the molecules in the sample. This means that there are more molecules with enough energy to overcome the activation energy in a given sample, so successful collisions are more likely to occur. So we see this from this kinetic energy diagram here, which shows the fraction of molecules at different kinetic energies. So for a lower temperature, T1, here is the average kinetic energy, and there are however many molecules, fraction of molecules in the sample on each side of this. And at the right kinetic energy to overcome the activation energy, we see that there is a small amount of the sample, a small fraction of molecules that have enough energy. Whereas at a higher temperature, with a greater average kinetic energy, we see that there is a much greater fraction of molecules that have the right kinetic energy to overcome the activation energy. So there are more molecules that are moving faster. On average, the kinetic energy is faster. So there's a greater fraction of molecules with the right activation energy. So more successful collisions are able to occur. Basically, a greater temperature means more successful collisions because there's a greater fraction of molecules at the right activation energy. So now we're going to look at how we can relate the rate law to the temperature of reaction, and we're going to use the rate constant to do this. And we're going to use the Arrhenius equation to relate the rate constant to temperature, and then we can use that to relate temperature to the rate law. Savant Arrhenius developed a relationship between the rate constant and the temperature that the reaction occurs at, known as the Arrhenius equation. So here we have the Arrhenius equation, which compares two different rate constants and their temperatures. So we have ln K2 over K1 is equal to negative EA over R times 1 over T2 minus 1 over T1. So K1 and K2 are the rate constants at two different temperatures. As we said before, rate constant changes depending on the temperature. As well, we have EA, which is the activation energy. This is constant for a particular reaction. We have R, which is the gas constant. And we have T1 and T2, which are the two different temperatures that the reaction occurs at. So we can use these to compare the rate of reaction at two different temperatures. So let's see it in action. We're going to compare the rate of reaction of the decomposition of dinitrogen pentoxide at room temperature, and then again at 305 degrees Kelvin. The activation energy is 106 kilojoules per mole, and the rate constant at 298 degrees Kelvin, which is room temperature, is 3.46 times 10 to the minus 5. So we're going to see how we can use the Arrhenius constant, and we're also going to show how different temperatures will affect the rate constant and then the rate. So we remember our rate constant equation is ln of K2 over K1 is equal to negative EA over R times 1 over T1 minus 1 over T2. So because we're looking for the K's in this particular reaction, we're looking for K2. This is K2, K1. Sorry. Because we're looking for K2, we're going to take instead e to the power of this whole thing so that we can isolate K2. So K2 over K1 is equal to e to the power of minus EA over R times 1 over T2 minus 1 over T1. And then we're going to multiply this whole big e to the power of this times K1 so we can fully isolate K2. So K2 is equal to e minus EA over R times 1 over T2 minus 1 over T1, all of this times K1. And we're going to then plug in these numbers so that we can get an answer. E, and we know that the will be joules per mole. We know that the rate, the gas constant is 8.314. Our T2 is 305. Our T1 is 298. And we're going to multiply this whole thing by the rate constant, which is 3.46 0.46 times 10 to the minus 5. And when we do all this math, we should eventually get that K2, just do the whole thing, see if you get the same answer. We will get that K2 is, we'll get that K2 is 9.63 times 10 to the minus 5. And when we look at here, we'll see that basically as long as the concentration for NO2, N2O5, nitrogen pentoxide, is the same, no matter what, because the rate constant is so much higher for the greater temperature, this one is always going to have a greater rate. So basically we've shown now theoretically and mathematically that at a greater temperature the reaction will always occur at a greater rate. Thank you very much for listening, and I hope that you learned something.